All right, we're going to try. Usually I keep these next two sections together because they deal with how to graph, using calculus, how to graph functions. Because in algebra, how do we graph functions? Well, we find the x-intercepts, we find the y-intercepts, and then we know what the shape is. Then we start plotting points. Well, now we go a little bit further. With calculus, we can not only find to graph functions, you need the x-intercepts, which are the solutions. You need the y-intercept. You have to know the end behavior. The shape of the curve. The maximum number of x-intercepts. The max numbers of vertices. Locations of the vertices. And the direction of the curve on both sides of a vertex. Where the curve changes directions. There's a lot of stuff that we have to know. So let's see what we know already. We know how to find the x-intercepts, the solutions. Even if it's a larger polynomial, we could use the Descartes rule of signs. We can use the synthetic division, to the quotient of the division rule to figure out where the actual intercepts are. The y-intercept, just look for the constant. It's always the constant of a function. How do you know the end behavior? Look at the leading term. The leading term is the one with the exponent. You have this as the leading term. The degree of the leading term tells us what? If it's even or odd. If it's even, then both ends point up or point down. If it's odd, then they point opposite. All that is dependent on the coefficient. So if A is positive, it goes up. If A is negative, it goes down. If A is positive, it's increasing. If A is negative, it's decreasing. Yeah, all this stuff is reviewed from algebra. So these tell us the shape of the graph. How do we know the maximum number of x-intercepts? Maximum what?
Like
Yes, exactly. Yes. It's whatever your degree is minus one. For example, a quadratic equation is degree 2, n equals 2. So n minus 1, there's only one vertex. Oh, no, the maximum number of intercepts is the n itself. The maximum number of vertices is n minus 1. So the degree tells us the number of x intercepts we can have. For example, the vertex, the quadratic has 2 possibilities, or have 1 or have 0. Because remember, this if n is even, you can have, let's say, for example, n equals 2. We can have 2 solutions, we can have 1 solution, or we have no real solutions. If n is odd, let's say it's 3. We can have 3, we can have 2, we can have 1. But we have to have at least 1 for odd degrees because they point opposite directions. All this stuff sound familiar from algebra? How do we find the vertices? Once we find the vertices, what happens to both sides of the vertex? And then where does it change direction? For example, like in the cubic function. In the cubic function, we have something like this. What I meant by direction is concavity. Notice how this side of the graph is pointing down. That's concave down. Here, it's a bowl. It's concave up. So that means there has to be a point somewhere between there where it stops going down and starts going up. That's what we're going to figure out. Because that's where the shape begins to change the shape of the direction of the flow. Look over here. The direction of the curve on both sides of a vertex. What does that mean? Let's look at a quadratic equation. The vertex, in this case, is the lowest point. What's happening to the curve to the left of the vertex? What direction is the graph going? It's going down. The slopes are going down. On this side, it's going up. So if we have a minimum, then we know that on the left-hand side, it's got to be going down, and on the right-hand side, it's going up. That's how it's the minimum. If it's a maximum, what happens? On the left side, it's got to be going up. On the right side, it's got to be going down. Let's put mathematics to all this. So pretty much everything algebra is done up to here. 7, 8, and 9 is what we're going to do today. This is in section 3, and this is section 4. That's why I keep them all together. Let's go. So the first question I have is, how do we find the vertex point? Well, I should say vertex itself. How do we find the vertex using calculus? Yep. The derivative of the function is equal to 0. Why is that the vertex? And why is that the vertex? Right. Because at that point, it's a horizontal line. M equals 0 is a horizontal line, which is where a vertex is. And the slope is the first derivative. Very good. So now we're connecting calculus with algebra. Calculus is derivatives, algebra is slopes. So if we have a minimum, what's happening to the left? What's the slope to the left? Yeah, on the left, the slope is less than 0. Or the first derivative is less than 0. On the right-hand side, the slope is positive because it's going up. That means the first derivative is positive. Which is what we see on our sheets, what we call corollary 3. F is continuous and differentiable on a closed interval. It says it's continuous on this closed interval and differentiable on the open interval. The reason being because what if you can't use the endpoints? We have to go back to the beginning of the semester for that. Remember this example? We went from -2 to 2. In order to take a derivative at a point, what has to be true? 3 things have to be true. Can you remember what they were? It's got to be continuous. Okay, if it's continuous, yes. Okay, then what about what else? How do we define derivatives first? Before we find it as slope, we defined it as what? Using what math theorem? The limit. In order for it to be differentiable, it has to have a limit, and the limit has to exist from both sides. Well, we can't really go to it from this side. So that's how come, if it's differentiable, it could be, because we can't really use -2. So that's what we're saying there. So it's got to be continuous on the entire closed interval, differentiable on the open interval, at each point. Then we say that f is increasing if the first derivative is positive on that closed interval. F is decreasing if the derivative is less than 0 on the closed interval. Instead of if, I should be saying where it's positive or negative. Instead of if, because when is the only time it won't be positive or negative on a slope? If it's a horizontal line, if the slope is 0, then it's neither increasing or decreasing, it's slope 0. So that's right. Instead of if, I should be saying where the derivative is positive or negative. Because that's corollary 3. That's going to help us now figure out where a function, the vertex, exists. Because if the slope is 0, we find the x value. Once we find the x value, plug in the function, we get the y value. So we have the vertex point. which is very difficult to do in algebra. So let's look at example 1. Find the critical points. Okay, we have to find something else here. Before we do example 1, we have a couple things. A monotonic function and critical points. A, a monotonic function is if it is only increasing or only decreasing. That's monotonic. Like a linear equation. It's either always increasing or always decreasing, or the cubic function. If it's monotonic, it doesn't have a vertex. So monotonic functions are always increasing or always decreasing. There's no change. Critical points are the x values where the first derivative equals 0, where the slope is 0. Which means it's the x coordinate of the vertex. Why do we use critical points? How are critical points used? Let's say we have a function x squared plus 5x plus 6. We find the first derivative and set it equal to 0. What do you think we do next? Solve for x. So we have 2x equals negative 5, x equals negative 5 over 2, or negative 2 and 1/2. So there's negative 2.5, or 2.5. That is our critical point. Because we know at that point the slope is 0, which means at that point, up somewhere up and down, we have the vertex. So that's our critical point. How do we know whether it's maximum or minimum? If it's maximum, if the critical point is a maximum, then what has to be true? If it's a maximum, there's a point. It means it has to be the top of a curve. That means then the first derivative has to be less than or greater than 0 on points to the left of the CP, and has to be negative on the points to the right of the CP. So remember, the critical point, let's say our critical point is right here. It's -2.5. So how do we determine if it's a maximum? Well, we pick a point to the left of it. We pick a point. Is that mine? Or yours? So we say pick -3. Plug -3 into the first derivative function, and we should get a positive number, say 2. Since it's positive, it's greater than 0, we know it's increasing. That means all points, since we only have one critical point, all points to the left of it, in this case, are going to be positive because the slope is positive. And then we pick another point. Let's say it equals -3. That's less than 0. So that means all points here are pointing down. They have a negative slope. Then because of that, on left side is up, right side's down, so it has to be a maximum. That's how we use corollary 3 to find the critical points and begin to start defining our shape of our curve. So now let's go back to example 1. Find the CP of f of x equals x cubed minus 12x minus 5. And identify the open interval where f of x is increasing and decreasing. Okay, here are the steps. First step, what do? Yep. Find the first derivative. So this is step 1. F prime, what does f prime equal? 3x squared minus 12. And then that's a constant, disappears. Second step. Set it equal to 0. This is step 2. Step 3. Solve for x. That will be your critical point or critical points. So we have 3x squared equals 12 divided by 3 squared. So what does x equal? Because we have to have two solutions. So those are our critical values. Okay. Now what do? We know on our number line our critical points are here. Examine what f prime is doing in each interval. How many intervals do we have? There's one there, there's one there, and there's one there. So what we have to do is we have to find x values for each of those. All right, so our intervals are from negative infinity to -2, between -2 and 2, and from 2 to positive infinity. Because our critical points were -2 and 2. I should put it here, -2 and 2. So what do you think you do next? Well, choose a point. Take a test value. This is step 5. Step 5, choose a test value in each interval. So pick a point in this first interval. What do you get? I always pick a one close to the very end, so -3. How about between -2 and 2? What's the best, easiest one to pick from there? 0. If you ever use 0, use 0. That's the easiest one. And on this one, 3. Those are my test values. What do I do with my test value? Plug them into the first derivative. First derivative was 3x squared minus 12. So we have 3 times -3 squared minus 12. 3 times 0 squared minus 12. 3 times 3 squared minus 12. -3 squared is 9. 3 times 9 is 27. 15. 3 times 0 is 0. And we get the same thing. So what does this tell us? Remember, this one, our first derivative is positive. This one's negative, and this one's positive. So at -2 and 2. On the left-hand side, what's the slope of the curve? Is it going up or down? It's positive, so it's going up. On this interval, the slope is negative, so it's going down. And at this interval, it's going up. It doesn't tell us the x-intercepts. We have to do that algebraically or using some other method. But we do know that at -2 and at +2, which one's this? Is a max or a min? Absolute, local, global, relative, local and relative, same thing. And this one is a min because it's the lowest. And to be honest with you, that pretty much this little short excerpt we had there, that covers that whole section. Let's just do the rest of the examples. So find me the location. Okay, just by looking at our original equation. Remember, our original equation was x cubed minus 12x minus 5, I believe it was. Yeah. What else can you tell me about my graph? What intercepts can you tell me? Only one you can tell me is this one. It's got to cross at -5. What else can you tell me with this equation? Yeah, I mean, finding the x-intercepts with that would be pretty difficult. So you can't, well, you could if you use the Descartes rule of signs, the difference quotient, and everything else that. Not this question, but the difference rules of sign. What we know is our maximum minimum occur at -2 and 2. So at f of -2 and f of 2, we know the actual location of our maximum minima. So -2 cubed minus 12 times -2 minus 5. 2 cubed minus 12 times 2 minus 5. Work those out and they'll tell you the actual locations. We can tell that this one's going to be at -2. This one's going to be at 2. So it's -8 plus 24 minus 5. So -13 plus 24. So we know one vertex is at -2, 11. And the other one is at -21. So the only thing we have to do then is figure out the x-intercepts and plot a couple extra points. We know what the graph's going to look like. It looks something like this. Actually, negative 21 is further on down. That's the reason it doesn't cross through the origin, because the y values are not equal. So since this one's really farther down here, between those two, that's where it crosses. So far, so good. Let's look at example 2. And what we just discussed there has a name. That's called the first derivative test. The first derivative test is taking the first derivative, find the maximum minima points, and determine whether they are the maximum minima. X to the power 1 over 3, x minus 4. Find the critical points here. And let's go further and tell me whether they're maximum minima. How do we do that? Okay, what method are you using first? If you're using the product rule, that's not wrong. It's just going to take you more time. Don't feel bad, because that's typically the first thing you look at. It's a product. What if we went ahead and multiply these two out together? This times this is going to equal what? You have x to the power 1/3 times x to the power 1/3 times 4. So what's this going to equal? That's 1. You add order of exponents, the properties of exponents. If you have the same bases, you add the exponents. So this is actually 3 over 3. So we get x 4 over 3 minus 4x to the power 1/3. The reason this would be easier is because now we can take the derivative of each of these separately. I don't have to do a product rule or a quotient rule or anything like that. So the derivative is equal to 4/3 x to the power 1/3. Remember, the rule is this. For derivatives, bring the power down, subtract 1, which is 4 minus 3, or 4 over 3 minus 3 over 3 is 1. The second one is 4, bring the 1/3 down. Subtract that, you get negative 2/3. Just 4 to the power 1/3 over 3 minus 4 over 3 x 2/3. What do you have to do to combine them? No, but well, they both have a 3. You have to have a common denominator. They both have a 3. This one has an x 2/3. This one needs an x 2/3. Yeah, But if you do the cross multiplication, you'll send up the same thing. You just see what's missing. So we multiply x to the 2/3 times x to the 2/3. So now we have a common denominator. What do we have on top? What does this one become? One-third plus two-thirds is what? Which is which can be simplified. We can factor out the 4. So that's our first derivative. Now what do you do with it? Set equals 0. The critical points or critical values are any x value that makes the numerator equal 0 any x value that makes the denominator equal 0. In other words, any asymptote, vertical asymptote point is a critical point, critical value. Do you understand why? We're looking for to see where the slope is 0, right? That's an important point. That's where the top equals 0. But any x we can't use is also an important point because that defines our intervals of x's we can use. So we have 0 equals 4x minus 1, 3x to the 2/3. So the numerator, we have x minus 1 equals 0, x equals 1. That's one of our critical values. The denominator, x 2/3 is equal to 0 when x is equal to 0. So these are our two critical values, but we cannot use that in our final answer. That's why our intervals are also parentheses. So let's look what this looks like. At 1 and 0. So these are our critical, that's an asymptote. We can't cross that. And this is at this point here somewhere, we have a critical value, critical point. We know that the point here, because we set the numerator equals 0, So what's going to be our critical point? What's going to be the vertex? What's the location of the vertex? What does this tell us? What does that mean? That's these critical points tell us, or the critical values tell us the x values of where the slope is equal to 0. Or where it's undefined. If a slope is undefined, what does it look like? What does that mean? It's a vertical line, or the slope is vertical. So we know that about our graph. So what else do we know? So we know at 0 something happens. What's let's look back at our original equation. Our original equation was f of x equals looking at this, what can you tell me? It's already factored out. If you set them both equal to 0, what would that tell you? It tells you your x-intercepts. Remember the first example we put that quadratic, x squared plus 5x plus 6. That tells us where the x-intercepts are. And then between there, we can tell them what the slope is going to look like. So we know our x-intercepts are at 0 and at 4. And we know our vertex will be somewhere on this line. And the line is vertical here. So what do we do next? Look at the steps. We found our critical point values. Now what do we do? Look at the steps. You have them written down. Hope that's the reason you wrote them down. What do they say? After you find your critical values, what do you do? Hmm? That gives us our intervals. We have to know what this graph is doing in those intervals. Is it increasing or decreasing? So in the first interval, we go from negative infinity to 0, then from 0 to 1, and then from 1 to infinity. What is the graph doing in those three intervals? Because we're looking at between 0 and 1. So here I'll take negative 1, I'll take 1/2, and I'll take 2. Plug in the test values. in the first derivative. And that's going to tell you the direction of the graph there. Is it increasing or decreasing? Is it going up or is it going down? So remember, the function for the first derivative, well, x minus 1 over 3 x to 2/3. Plug that in there. So we have 4, -1 minus 1, -1 to the 2/3, 4, 1/2 minus 1, 3, 1/2 2/3, 4, 2 minus 1, 3, 2. Now, why would I would rather use the 0.8 there. Why would that be better for me? Because of the 2/3. This means cube root. We can't use 1. The next perfect cube root is 8. So I pick values of what's going to be easiest for me to use. So 4, -1, -1 is -2. The cube root of -1 is -1. -1 squared is 1. So it's -8 over 3. So on this side, the graph is going down. So it's -8/3, which means it's going down. 1/2 minus 1 is -1/2. Okay, the value, the number is irrelevant. All I want to know is it going to be positive or negative. The bottom can never be negative because it's squared. The top, since it's negative, the whole thing is going to be negative. So here it's going to be decreasing also. Four times 7. Cube root of 8 is 2. 2 squared is 4. All of those are positive. So at this part, it goes up. So we know the shape of the curve. It's going to go down here. It's going to go down here. And from this side, it's going to go up. It's got a cross there, and it has to cross there. Those are my intercepts from this. Well, let's find at x equals 1. At x equals 1, y is -3. So the graph will look something like this. Or maybe it's a curve. That's what the graph's going to look like. But again, we need more points to know exactly what it looks like. But we know that the first derivative tells us it's decreasing here, it's decreasing here, and it's increasing on this side. Let's look at example 3. Find the critical points of f of x equals x squared minus 3 e to the power x. So it says, yeah, find the values. So tell me where, yes, that's good. So how do I do that? What do you notice about this function? Yeah. Well, yeah, we look at this as two functions. Why is this different than the first one we did? Because of the e. No matter what we do, we're going to have to use the product rule. Even if we distribute it, we got to use the product rule. So I might as well use the product rule with this. So it's x squared minus 3. The first derivative is 2x. E to the x. What's the derivative of e to the x? E to the x. So it's going to be 2x e to the x plus x squared minus 3 e to the x. Distribute that. Actually, since they all have e to the x in common, it's a quadratic equation. It looks like it's quadratic. So hopefully there's a factor. What signs go in there? Yeah, so second sign is a minus, one's positive, one's negative, and the bigger number gets the plus. What times what is 3? When you subtract them, you get 2. 3 and 1. Now it's easier to look at. Because we know that e of the x, what do we know about that one? Does it have an x? Where's the x-intercept for that one? E to the x is a increasing function. It never crosses the x-axis. It can never be negative. It crosses on the y-axis, but does not have an x-intercept. So our only x-intercepts are at -3 and 1. And not x-intercepts, I mean critical points. Because this is if we set it equal to 0. Those are the only zeros we'll have. So these are my CPs. So we have a critical point at -3, and we have a critical point at 1. So those are our intervals. What do you do next? Choose some test values. Right. So what test value you want to put in the first one? Yeah, -4. Because it's not a fraction, it won't matter. How about the next one? 0 and 2. Which function do we plug those in on? The derivative, right? So f prime at -4, f prime at 0, f prime at 2. And we can go ahead and use, well, there's the original functions up there. So original function was x squared minus 3 e to the x. -4 squared minus 3 e to the -4. 0 squared minus 3 e to the 0. 2 squared minus 3 e squared. So this one says -4 squared is 16 divided by e to the 4th. 13 divided by e to the 4th is positive. -3 times 1. This is negative. Four times 3, e squared. Positive. So it's e squared, -3, 13 over e4. So since it's positive, we know it increases. If it's negative, we know it decreases and it increases. This is an interesting function. If you graph this function, where are our x-intercept? So where do we have an x-intercept? Look at the original function. Set this, because this one can never be 0. So we set this one equals 0. So x squared equals 3. X equals plus or minus square root of 3. So we know we have square root of 3 is less than square root of 4. So it's got to be less than 2. So it's got to be somewhere around here and here. So those are the x-intercepts. We have our critical values at -3 and 1. So those have to be vertices. At 1, our vertex is going to be 1 squared minus 3 e to the 1. So -2 e to the 1st. So it's going to be down here somewhere. This is going to be negative. That's a y-intercept, so it has to be increasing. And this thing says we're increasing from this side. This middle part between -3 and 1 is decreasing, and it has to cross through that. So this graph will look something like this. Because we have a vertex there. See the importance of knowing a vertex? Since we have a vertex at -3, it's increasing to the left of it, it's decreasing to the right of it, and it doesn't cross the x-axis anymore. You see how all these pieces fit together. So that's something what it looks like. So it's a decreasing function there. And then it looks like that. Now, you notice we don't know what this part looks like here. Because all this tells us whether it's positive or negative slope. That does it for that section. Now let's jump into the next section. What the next section does, there's a point between the maximum minimum points. There's a point between there somewhere where it changes direction. Somewhere here, it changes what's called concavity. And that's going to be, let me